So hopefully we have all worked some problems to become proficient with electrochemistry, setting up cell diagrams, figuring out who should be oxidized and reduced to get you a positive cell potential. It's time to do some math with all of these things outside of just adding up cell potentials. This is an equation that you have seen before. Delta G non-standard equals delta G standard plus RT ln of Q. Well, using an equation we've seen once before to relate G and electrochemistry, we can define delta G as negative NFE. That's delta G non-standard is E non-standard. We can define delta G standard by using the same equation but plugging in E standard. So if we substitute in negative NFE and negative NFE standard for those two things, we get this equation. And then solving this equation for E non-standard by dividing by negative NFE, we come up with this equation. This equation is called the Nernst equation. It says E non-standard is equal to E standard minus RT over NF times the ln of Q. R is our standard 8.314 joules per mole Kelvin. T is temperature in Kelvin. N is the number of electrons, remember, and F is Faraday's constant. It's a constant. Just like previously, G standard meant 1 atmosphere or 1 molar concentrations. E standard means 1 molar concentrations, 1 atmosphere as well. So anytime you need to measure a non-standard concentration, something other than 1 molar or 1 atmosphere, you have to use the Nernst equation. And hopefully you don't really need this reminder, but I'll put it here anyway. Q is the same as K, but at any time other than equilibrium, and that's products of reactants raised to their coefficients multiplied together. So this RT over NF, R is a constant and F is a constant. And frequently, we're talking about systems at room temperature or 298 Kelvin. So the Nernst equation is sometimes seen in this simplified form, where you've plugged in R and F as the constants and 298 room temperature. You'll see that sometimes, but you'll also see it this way. What's the difference in these two? Well, an ln and a log is related by this equation. So you'll see an ln of Q or a log of Q as two versions of the Nernst equation at room temperature, but the constant here is different whether you use ln or log. Pick one and stick with it. Both are correct, both are fine. So let's do a problem where we're going to need to use the Nernst equation. What is the calculated potential for the system described here between nickel and palladium? First of all, you need to find the appropriate rows in your reduction potential table. There's our nickel row. And it took me a second to find palladium, but here's palladium. Sometimes things appear twice in the table. Make sure you're looking at the appropriate row. See, here's iron above and below, but one is iron 3 plus becoming 2 plus and 2 plus becoming solid. They're different equations. Make sure you're checking carefully. So if we're going to combine palladium and nickel together to get a positive potential, palladium is already positive. If we flip nickel so that nickel becomes oxidized, that gives us the most positive potential possible between those two systems. So that's going to be nickel solid. I need a little more room to write, so we're going to the big screen. Nickel solid plus palladium 2 plus yields palladium solid plus nickel 2 plus. Hopefully you recognize who's the cathode, who's the anode. Yeah. We said the most favorable way to combine these is in this way because it gives us an E standard, E naught, of 1.25 volts when nickel is being oxidized and palladium is being reduced. So we're going to use the Nernst equation, and my favorite version is this one. I've got 1.25 volts minus 0.0257 over 2, because there are 2 electrons being exchanged in this system. Ln of products over reactants. So that's nickel over palladium. Why did we not include palladium solid or nickel solid? Solids are not ever found in Q expressions. So this becomes 1.0 divided by 0.017. Do a little plug and chug of this thing and see what we get. I got 1.198, 1.20 volts. It's always nice that you can double check these if you remember some equilibrium details. So if both of these ions were 1 molar, that would mean K equals 1. And where K equals 1, you're at equilibrium. And basically that's saying that when both of these are 1 molar, this should be your voltage. But since palladium concentration is smaller than nickel concentration, we can say equilibrium would shift to make more of the reactants. If equilibrium shifts left, our voltage goes down. If equilibrium shifts right, our voltage goes up. That's kind of cool. So if we take a look at a new example, this system is silver and silver. Do you get electron flow between 2 silvers? Yes, if they're different concentrations like these are. We have arrows already on our wire that tell us electrons are flowing from the less concentrated to the more concentrated. This is our anode. This is our cathode. So if we look at a cell notation, that's this. Why can we say E cell standard is 0? Well, the reduction potential of silver is 0.8. And if you reduce silver and oxidize silver, it would be negative 0.8 and positive 0.8. It's 0. So if we did the whole Nernst equation, E cell equals 0 minus 0.0257 over 1, because we've only got 1 electron in a silver plus, ln of products over reactants. The way a cell diagram is written, this is a reactant, a product, a reactant, a product. So it's this thing on top and this thing on bottom, products over reactants. Whoops, no 0 here. 0.1. We get that this cell should measure 0.0592 volts. Not a very big voltage when you just have a concentration difference like that, but a voltage nevertheless. This system is silver nitrate. The silver ions are being oxidized and reduced in each side of this thing. But instead of a salt bridge, this time there's a porous disc. It has the same type role, but nitrate ions are going to flow through this porous disc. Which way are they going to flow? This anode side is becoming more positive because our silver is becoming silver ions on this side. So our nitrate actually flows toward the anode. Anions flow toward the anode. Yep. The reason they do that is to keep things electrolytically charged. Where have you seen this before? The sodium ion concentration in nerve cells. Sodium potassium pump. That should ring a bell. Hopefully you're talking about the same thing in cell biology right now. Another example of how the Nernst equation can be used is here. We can measure the voltage of a system to determine the concentration of an unknown ion in solution. What? If we connect copper to a standard hydrogen electrode, remember a standard hydrogen electrode is our zero reference point. We can have a system that looks like this. The voltage we're told it measures is 0.313 volts. The standard reduction potential of copper is 0.34 volts. So when you combine the She with copper, copper has to be the cathode because copper has to be being reduced in order to get a positive voltage overall. So we have this cell notation down here where copper is the reduction half, hydrogen is the oxidation half, and we can set up our Nernst. So the Nernst is E equals E naught minus 0.0257 over N ln of this time H plus squared, it's been a while since we've had to do something like that, H plus squared, because that's the coefficient, times Cu2 plus, or divided by Cu2 plus, concentration of Cu2 plus. I'll get it eventually. So we know that the actual measured voltage is 0.313 volts. Standard would be 0.34 volts. 0.0257, we're at room temperature, so this is legit. There are 2 electrons being exchanged between these guys. Ln of 1 molar, H plus squared, but it's not going to matter, over X. You may not want me to, but if I walk through the math details, 0.027, negative 0.027 equals negative 0.01285 ln of 1 over X. Ln of 1 over X equals 2.101. E to the both sides, I get 1 over X equals 8.18. So X equals 0.122 molar. If we go back to our original, we found our copper concentration to be 0.122 molar. You can actually confirm and verify that this is at least in the right ballpark, as in less than 1, because your measured voltage is less than your reduction potential would be. So it means equilibrium is favoring the reactant's side, which tells me my copper concentration has to have been less than 1 molar. The Nernst equation. You'll like it.